Another example of being able to use a local linear approximation to estimate a value. This time we have a little bit more complex function. So we have 1 over the cube root of 216 plus x, and we're considering an routing point a equals 0. All right, so just like we did in the last video, we are going to find L of x, the local linear approximation. We're going to approximate f at point 1 using the local linear approximation, and then we're going to find the percent error to see whether or not we get a decent approximation or not. All right, so we know right away that x naught is going to be equal to 0. And then y naught is going to be found once we plug in 0 back into the 1 over cube root of 216 plus 0. And that's going to give us 1 over the cube root of 216, which is just going to be 1/6. All right, so that's nice that it doesn't turn into a weird decimal or anything like that. And then the other thing that we need to do is we need to figure out what the slope is for this. Okay, so, and then we're going to substitute 0 back in. So we're going to find the derivative. And to find the derivative, what we should probably do is we should start by setting this up as 216 plus x to the minus 1/3 power. Right? And then from there, what we can do is we can go ahead and find the derivative. So this is going to be our f prime at x. So that's going to be minus 1/3 216 plus x to the negative 4/3 power. And the nice thing about this is that the derivative of the inside is just going to be 1 if we were to use the chain rule on this, which we should consider, but it's not going to be consequential because 1's an identity. Now what we can do is we can go ahead and just move this back into a nicer form. So this is going to be f prime at x is going to be equal to minus 1 over 3 cube roots of 216 plus x to the 4th power. All right, so that's going to be our derivative for this. And now what we're going to do is we're going to find the slope when a is equal to 0. Okay, so we're going to get that f prime at 0 is going to be minus 1 over 3 cube roots of 216 plus 0 to the 4th, which is really just 216 to the 4th. All right, and there's 2 ways to do this when we try to approximate or to try to evaluate this. So this is really 216 to the 4th. Now, if we go to our calculator and we try something like 216 to the 4th power, it might give us a really big number. So let's give it a try. So we have 216 raised to the 4th power. All right, and that's going to be this number. And then we're going to take the cube root of that. All right, so we're just going to raise this to the 1/3 power. All right, that's going to give us 1296. Another way to do this is to take, so just remember that number 1296, it's right here. We could go ahead and just take 216, take the cube root of that, so raise it to the 1/3 power, and then just raise 6 in this case to the 4th power. And we should get the same number, the 1296, which we do. All right, so if you're doing things by hand, it's usually easier if you take the root first and then do the exponent. All right, so that way you get a smaller number to take the exponent of, rather than taking the exponent of a big number and get something weird. All right, so anyhow, this is going to work out to be negative 1 over 3 times 1296. Okay, and then we can just throw that in our calculator one more time. So we just multiply this by 3, and it should be 1 over, or negative 1 over 3888. All right, now that's our slope. All right, now for us, what we have to do is we have to find the equation of that tangent line. Okay, and so we're going to find our L of x, which is going to be the slope, which we just got to be that negative 1 over 3888. We're going to have negative 1 over 3888. And then we have x minus x naught. And fortunately for us in this case, x naught is going to be 0. And then we have the 1/6 for y naught. All right, so we don't necessarily get a really nice number out of this, but it could be a lot worse. So L of x is going to be negative 1 over 3888x plus 1/6. All right, so that's nice that we have this. All right, so that's our linear approximation. Now we can start to do the rest of the stuff that we need. All right, so we're going to approximate f at 0.1. All right, and that's going to be easy because we just plug in 0.1. So for part B, we find L at 0.1, which is going to be negative 1 over 3888 times 0.1 plus 1/6. Now we're just going to go to our calculator. All right, so let's clear everything out. So we have 1 over, or negative 1, excuse me. So we're going to have 1 negative over 3888. And then we're going to multiply that by 0.1. And then we're going to add that to 1 over 6. All right, so we get this 0.166640. All right, so this is going to give us approximately 0.16666409. All right, so we're going to hold that. Right. Now this is going to be our approximation. All right, to get to the actual value, okay, what we're going to do is we're just going to substitute 0.1 back into the original function. Okay, so then we can start doing part C. Right, so for part C, we're going to find f at 0.1, which is going to be 1 over the cube root of 216 plus 0.1. And that's going to give us our exact value. And we're hoping that it's pretty close to this number, that 0.16664009. Let's see what we get out of this. So go back here. We are going to clear this. And we're going to have our 1 divided by, let's just say 216.1. And we're going to raise that number to the 1/3 power. So we do the cube root of that. Oh, not 1 over 6, 1 over 3. All right, and we close that out. And it gives us 1.666409.5. So that's actually really close. All right, so the approximate value is going to be 0.1666. And it said 4095, so it's actually 410. All right, so this is going to be, we'll just use this as the exact value. And as you could see, the percent error is going to be really, really small between these two. All right, so let's clear a little bit of room out here. So we can go ahead and finish this out for our part C. All right, and we can just find our percent error really nicely with this. So for our percent error, we are going to have the absolute value of the approximation, which is the 0.16666409. We're going to subtract that from, I'm going to say that this is the exact value, 1.166410. Right? And then we're going to divide that by the exact, which was 0.166410. And then we're going to multiply that by 100%. All right, so we're just going to shove that in the calculator at this point. So let's clear this out. It's going to be a really small number. So 0.16666409 minus 0.16666410. And notice right away how small that is. We're going to divide that by 0.16666410. All right, so we get this number, which is scientific notation. We're going to multiply that by 100. And that's our percentage. All right, now we're going to move the decimal point 5 places to the left. We're going to ignore that negative sign because everything's an absolute value. And so if we move the decimal point 5 places to the left, let me just scooch this over just a little bit so we have some room. This is going to be 0.00006, and we could say 600. All right. and this is a percent. All right, so the moral of the story is that there's almost no error with this by using the local linear approximation. All right, and by the way, this is a pretty nasty function to try to deal with. All right, it's not the worst one we could deal with, but it's not the nicest one we could deal with either. All right, so in the next video, what we're going to do is we're going to start taking a look at some of the ways that we can use the local linear approximation to be able to estimate some square roots and some other types of roots. And then we're going to move on to differentials.